Hello everyone, and thank you for joining today's webinar. My name is Reese and I'll be your moderator today. We're going to kick off today's session in a couple of minutes. We're just waiting so everyone has a chance to join. In the meanwhile though, we'd love to hear from you, so let us know where you're joining from using the chat or the comments depending on what platform you're watching on. And yeah, tell us something that you'd like to get out of today's webinar. A few bits of housekeeping before we kick off. The session is being recorded and the recording will be emailed to everyone that is registered for the event. If you haven't registered already, head over to datacamp.com/webinars and I'll also be sending a link so you can find the exact event itself in the chat shortly. So yeah, keep your eyes peeled for that, and I'll also put a QR code on screen as well. We are going to have a Q&A at the end of the session today. We may also have one midway through. So yeah, if you have any questions at any point, then please let us know in the chat and the comments and I'll save your questions for the Q&A. Brilliant. I think that's everything from me. Keep your eyes peeled for the links that I send shortly. But until then, enjoy the background music. Hello everyone, and thank you for joining today's webinar. My name is Reese and I'll be your moderator today. We're going to kick off today's session in about 30 seconds or so. We've just been waiting so everyone has had a chance to join. Let us know where you're joining from using the chat, the comments, depending on what platform you're watching on. And yeah, tell us something that you'd like to get out of today's webinar. Quick note for anyone that's just joined, the session is being recorded and the recording will be emailed to everyone that's registered for the event. If you haven't registered already, then you can scan the QR code that I've put on screen now. And you can also find the link that I've put in the chat. I'll also be sending it again in a minute or so. Aside from that, you can also head over to datacamp.com/webinars and register there, as well as see all of our future events. We are going to be having a Q&A at the end of the session today, so if you have any questions at any point throughout the session, then let us know in the comments and we will save it for the Q&A. So yeah, you don't need to wait until the Q&A. Send us your questions as soon as they spring to mind, and yeah, we'll get them answered. Brilliant. I think that's everything from me, so now I'll hand you over to your host for today's session, Richie. Richie, please take it away.
Welcome to the webinar. This is Richie, and happy Thanksgiving. I've been looking through the chat, seeing where everyone's from. I'm curious if there are any Americans in here who are just hiding from their families right now. But with that, let's get started. So my background is data science, and for me, it's nice to think, okay, I've created some kind of model, I'm done. But of course, in many business contexts, that's not true at all. You need to then put the model into production for it to have any kind of value. And with the rise of deep learning models and large language models in particular, these require so much compute power, particularly from GPUs, and this creates additional challenges into getting things into production. So today we're going to cover a lot of the practical issues around putting these models into production. And our guest is Ronan Dar. He's the Chief Technology Officer at Run AI and also one of the co-founders. And Ronan is helping build an infrastructure platform for enterprises to manage AI workloads and simplify their AI journey. He's previously worked as an engineer and researcher at Apple, Intel, Bell Labs, and Tel Aviv University. So without further ado, over to you, Ronan.
Thank you, Richie. Thank you for having me here. So first of all, hello everyone. Happy Thanksgiving to everyone who was celebrating and just, as Richie said, they ran away from their families. Um, so excited to be here, and let's speak about LLMs and best practices of putting LLMs in production, and also some of on training LLMs. We'll also discuss that. Let's do it as interactive as possible, right? So I'm tracking your messages, questions, so feel free to interact, ask questions. I will try to answer them, and let's have it as interactive as possible. So a little bit about me. So, hi, I'm Ronen Dar. I'm from Israel. I'm living near Tel Aviv, and I'm the CTO and co-founder of Run AI since 2018. Right, we started Run AI 2018. Before that, I did my PhD and postdoc, mainly in information theory, um, and I'm combining background in software, but also in hardware. So I've been in the industry in a couple of chips startups. So I know what's to build hardware, and I'm combining this background and expertise both in hardware and in software. And I think that's what led me and my partner Omri to start Run AI in 2018. Um, we saw that the cloud was built for running microservices applications on top of commodity CPUs. And we saw that AI is this new amazing technology. We knew that we want to be there, but we also saw that AI requires um, different software stack. AI needs something else. AI workloads are much more compute intensive. They run on those accelerators like GPUs. And we went on and started Run AI with the goal of building that software stack for AI clouds. And so that's Run AI, right? Like we like to view ourselves as the operating platform for AI. And what we do is we pool and share AI compute resources like GPUs across clouds and on-premise to deliver ML productivity for ML teams and more availability of infrastructure, more availability of GPUs, which is a big problem today. We raised $118 million, and we're working with the enterprises, startups across different industries, and we love our customers, and we're doing a lot with them, trying to help them move faster in AI. But I won't speak a lot about Run AI in this presentation. And I think I'll start with an intro on LLMs and the compute requirements for training LLMs, but also for deploying them in production. So I think the first part of the talk will be about LLM training, and the second one is an LLM inference. And we try to focus on what's going on under the hood, right? After, when training models and when putting them in deployment, what's happening in terms of the infrastructure of the GPUs, all of those things, and we'll try to give some best practices on how to train and deploy models. Let's start. So I think OpenAI, right? Like last year, this amazing thing. They introduced ChatGPT, and suddenly the amazing, powerful capabilities of language models were accessible to the entire world. And since then, we're having a lot of buzz, a lot of hype around AI. It just grew, right? And there is a big promise, big potential for AI. Everyone is seeing it right now, but there is also a big problem around compute power. And we saw this explosive demand for more compute power. Since then, OpenAI, after launching ChatGPT, they raised $10 billion for Microsoft. So that's a big number, $10 billion. And Microsoft, in their announcement, they mentioned 3 goals. And one was to build a supercomputer for OpenAI. The second was to use OpenAI models in Microsoft products. And the third was to be the exclusive cloud provider for OpenAI. And so most of that $10 billion goes essentially to cloud computing, just providing the compute needs of OpenAI for running all the models, training them, and running them in production. And we saw this in the last year, Gen AI startups raising billions of dollars for essentially for GPUs. Inflection AI raised $1.3 billion. Anthropic just recently raised $2 billion from Google and $4 million from Amazon. So it all goes to compute, to GPUs mainly. So big numbers. And we saw this trend of more and more computing power required to train state-of-the-art models. Here we see this trend. You see the training compute versus the time of those models when they were published. You can see that over here in the blue area and the green area, we're getting into the deep learning era. It's around 2012. Since 2012, we're seeing huge increase in the required compute power to train state-of-the-art models. It's actually 8 orders of magnitude increase in the last decade. So 100 million times more compute power is needed to train state-of-the-art models today compared to 10 years ago. So that's a big increase, big jump. And with LLMs are those the red marks over here. So LLMs require 2 orders of magnitude more compute power compared to traditional deep learning models. So 100x more compute power for LLMs. And it's not just for training, it's also for inference. We're seeing this rapid growth in the demand for GPUs for inference. These 2 graphs are from Meta's infrastructure. They published it earlier this year. So you can see on the left, the model size, that's the model size grows in terms, the model size of the models that are being deployed on Meta's infrastructure. So it's growing, but you can see the model size is the blue one. You can see like huge jump, 100x increase in the size of those models that are being deployed on Meta's infrastructure. And the purple or pink color is the compute requirement for those models running in production for inference. And you see like 10x more compute is required for just running inference in the last 3 years in Meta's infrastructure. On the right-hand side, you can see the demand for GPUs for inference workloads. That's the yellow curve. You can see this big jump in the last year. More GPUs are being used for inference workloads. So there is a huge demand for compute power also for just running those models in production. And what we see now is that companies struggle with compute for AI. Sam Altman had this amazing tweet, very famous tweet on speaking about the compute cost that they are eye-watering. It's a few weeks after they launched ChatGPT. The compute costs are eye-watering. Microsoft warned investors in their previous earning call that they might not reach their goals because they won't have enough AI chips, GPUs, to provide the needs of OpenAI and Copilot of GitHub. And it's not just the big companies, it's also startups. We saw in the last year this GPU shortage. The GPU shortage is real. And if you go and look for GPUs in the cloud today, and if it's the high-end GPUs like H100, you might wait for a few days until you could find an available GPUs. So it affects big companies, small companies, and it's difficult to manage GPUs. And we had this survey earlier this year. We asked companies, almost 500 data scientists, IT platform people on what are the biggest challenges when it comes to AI development. And the number 1 challenge was infrastructure-related challenges. Number 2 was compute-related. And data-related challenges were only number 3. So there are big challenges when it comes to infrastructure and GPUs. And we're seeing this shift in how companies and how people are consuming cloud resources. So from on-demand resources, just spinning up a GPU whenever you need it, companies are trying to secure themselves blocks of GPUs, securing access to those AI accelerators and reserving blocks of GPUs. And when it comes to reserving blocks and having like clusters, AI clusters, like clusters of resources, then the efficient operation of those clusters is key because we're seeing time after time when we're working with customers that when the clusters are not being operated efficiently, and you're getting this low GPU utilization. We typically see less than 20% GPU utilization in clusters that we work in when we start to work with customers. So think about it like infrastructure worth tens of millions of dollars, maybe hundreds of millions of dollars, and only less than a fifth of it is actually being utilized. And it means that also people are waiting for GPUs, right? Waiting to get access to compute. And that affects the productivity of teams and essentially also the quality of AI. So compute and managing clusters is a big problem. And let's go over training, right? Like how companies are actually operating their clusters for training, right? Training models on clusters of GPUs. And let's speak a little bit about how allocations are being done, right? Like I have a lot of resources. How can I allocate them to users and to my training workloads? And so what we see first is a very straightforward solution, right? A simple solution of just giving static allocations to users. For example, each user is getting a whole machine in the cloud, or each user is getting a whole workstation and next to his desk, right? So static allocations, simple and a simple way to allocate resources. But AI, as we see, it requires a dynamic access to compute. So we see here the profile usage of 4 users, right? How many GPUs they are using across time, so across several weeks. So those are actual 4 users on our system. And you can see that most of the time, users are quite idle when it comes to GPUs. They need just fractions of GPUs to run their Jupyter notebook, or so they can experiment with their data, debug their model, or things like that. But you can see that, for example, user 2 is in the first few days, like for a few days, is training is running a big model, a big job on 16 GPUs. So that's just one workload running 16 GPUs several times. But then that user is almost idle for weeks. User 4, for example, is idle for weeks as well, but then is launching a lot of jobs. You're seeing a lot of jobs which are running on more than 20 GPUs. So essentially, there is a need here for just queuing a lot of jobs and just launching them on GPUs. So you see, if user 2 and user 4 are sharing resources, that it's much more efficient for them than just getting static allocations. Because static allocations, either the allocation is too high, and then you're getting a lot of idle GPUs, or the allocation is too low, and people are limited by the compute resources that are given to them. So essentially, right, like idle GPUs, or people are not getting enough access to GPUs when there are like static allocations. And there is a need for like dynamic way of allocating resources, right? Like and just quotas that are being changed dynamically according to the requirements and what users need at every point of time. And there is also a need for this queuing mechanism to launch a lot of jobs. And what we so right, like sharing resources could be efficient. So we see also people trying to share GPU machines in manual ways. And what is AI cluster? Could it be used? I'm stopping one second because someone asked a question, and I like questions. So what is an AI cluster? So for us, AI cluster is a cluster with resources grouped together and are served for AI workloads, right? So a company having a bunch of resources and people internally want to train models or deploy models, so they do it on a shared cluster. So that's the way, as we see it, to have a centralized AI infrastructure, a centralized AI cluster where people can actually share resources and get more availability out of resources. And we'll get to that in a second, right? Because with static allocations, there is no mean of a cluster, right? Each person is getting their own allocation, and resources are not being shared. But if you try to share, then we see people trying to share GPU machines, then typically what we see is this people trying to share GPU machines in a manual way with Excel sheet or with Slack. But that's not fun to share resources in a manual way. But we also see that brings this problem of people hugging their GPUs, right? That's what we call it, like GPU hugging problem. People don't want to let go their GPU because if they will, then they will need to fight to get it back. So there's this need of like guaranteeing users access to resources whenever they need it. And sharing a GPU cluster, right? That's maybe that might answer the question. So trying to share a pool of resources between multiple users, that could have a lot of benefit in terms of just access to resources. So instead of each one having access just to a few resources, imagine that you could have access to a lot of resources if they were available. So just trying to share GPU clusters. And GPU clusters, right, to share them, you need some kind of an orchestrator or a scheduler. And the known solutions today for scheduling workloads on shared clusters of GPUs are twofold, I guess. So one is schedulers from the HPC world, from the high performance computing world, schedulers like Slurm, and the other is Kubernetes. And so workloads, the type of workloads that AI practitioners typically need is in interactive sessions, right? Interactive sessions with Jupyter notebooks or with PyCharm or VS Code, right? Just having an interactive session into resources in the cluster so people could debug and develop their code. There's a need to run batch jobs, right? Jobs that are just being launched on the cluster and being executed automatically. And there's also a need to deploy models, and we'll get very soon to what are the best practices on deploying workloads on a shared cluster. But Slurm and HPC schedulers were built for batch jobs. They are amazing for batch jobs. You can get them with them great results and essentially share a cluster. But they were not built for this interactive development sessions, and they for sure were not built for running inference services. A lot of tools are missing. So they're offering for those two workloads, interactive and inference, is quite limited. On Kubernetes, on the other hand, you're getting the opposite picture. So Kubernetes was built for running microservices, and there are a lot of tools like load balancing and auto scale, and a lot of tools to help to manage applications and services on top of Kubernetes. And those tools are very relevant for inference. And there are also a lot of tools when it comes to just running development sessions on a shared cluster in Kubernetes. So you can get like great results when it comes to interactive sessions and inference on shared Kubernetes clusters. But Kubernetes was not built for batch scheduling. And there are a lot of scheduling features that are missing from Kubernetes. And I'm listing some of them here. So we at RunAI, we believe that AI workloads should be scheduled in a smarter way. So while Kubernetes provides a way for running interactive sessions, jobs, inference, it doesn't provide these dynamic quotas, a way to guarantee resources to users. But think about it, there is also no way to actually to queue jobs and share resources in a fair way. Kubernetes supports a way, just a single queue, and people can't really share resources in a fair way. In Kubernetes, while you have just one queue, you might get into situations where one user can starve other users, and you need to start to limit users in terms of how much quota they get, how much resources they get. So just managing shared resources with Kubernetes is really difficult and really limited. And also gang scheduling, when it comes to running distributed workloads on multiple nodes, there are some limitations there in Kubernetes. Kubernetes was built for scheduling pods, not jobs. So I mean, like each distributed jobs composes of multiple pods. And when you're running multiple distributed workloads on a shared cluster, you might get problem where jobs are getting stuck and not getting enough resources. And so gang scheduling is limited in Kubernetes. And also in terms of GPUs, there are limitations in Kubernetes. So Kubernetes provides this dynamic way of provisioning GPUs, but you cannot really provision fractions of GPUs, right? If you just want to run your Jupyter notebooks on a fraction of a GPU, you can't really do that in Kubernetes. You can get just an integer number of GPUs, and you can't really over provision GPUs like you can do for CPUs. That's not possible today in Kubernetes. And we're trying AI, we're solving those problems both on the scheduling problems and in GPU provisioning aspects. So we've built an enterprise product with a dedicated scheduler that we plug into Kubernetes environment, and we essentially extend the capabilities of the default scheduler of Kubernetes, and we provide all of those advanced scheduling capabilities that are needed for shared AI clusters, like guaranteed quotas, dynamic quotas, queuing, fair share allocation, distributed training, and all of those things. And we're bringing also this layer of GPU optimization, where we enable fractionalizing GPUs and over provisioning GPUs. And we sit at the CUDA level and we intercept CUDA cores and we control the access to the GPUs, and we allow multiple workloads to get access to a single GPU. So essentially over provisioning GPUs with that layer. And we bring all the tools that enterprises and companies and startups need to control clusters, control resources, monitor resources, and also tools for researchers and ML engineers to just launch jobs, launch workspaces, launch their development environment on a shared cluster in a very easy way, right? So no one wants to deal with Kubernetes for launching jobs and launching workspaces. So we abstract all of that complexity, all of the Kubernetes complexity, and we bring very simple tools for people to interact on shared Kubernetes clusters. So we're doing all of that. Just a couple of slides about the results. So when we're working with companies, we're seeing this increase in GPU utilization once companies start to work with Run AI, and they share and pull the GPUs and start to work in the right way, and people are starting to run more and more workloads because they're getting access to more GPUs. So it's it in the GPU utilization. Typically, that's the curve that we see, that in a few weeks, GPU utilization grows from around 20% to much more than that. In this case, 3x improvement on the GPU utilization. So people are using their GPUs better, less idle GPUs. People are getting access to more GPUs, and people are actually launching more jobs, right? Like more experiment on that shared cluster. So in terms of number of workloads, we also see this trend of just more and more workloads being run on the same infrastructure, on the same resources. So in this case, almost 3x and more jobs being launched in a matter of a few weeks. So we're seeing that, right? So that's us. Last slide about us. A centralized GPU optimized AI infrastructure, shared clusters, so people can get more out of their AI clusters, more GPU utilization. Essentially, they get more access to more compute, so they can move faster, and they can do better model training, and so on. So we have also a community version, and for people who are not using Kubernetes, people who are just using bare metal resources, we call it GENV. It's a GPU environment management, and it's open source and free, and we're inspired by PyEnv and Conda, right? So we call it GENV. So it's very similar to how you create environments with PyEnv and Conda. So you can create your environments on GPUs, and so you can provision GPUs, bare metal GPUs, right? Like dynamically with fractions of GPUs also. And we're going to provide some more monitoring. So you could monitor the usage of your GPUs and metrics like GPU utilization and so on very easily. That will come very soon. So that's GENV. We have common integrations into common IDE tools, into Jupyter Notebook and VS Code. You can find us on those marketplaces. Okay, so that was on training. It was more on generic, training on shared clusters. But now we're going to get into the details of LLMs and how to deploy LLMs. So more interesting stuff here, and it won't be on Run AI. I see that let's stop maybe for a few questions if people have. I can look for the questions. Let's see.
Sure. So there's a question from Adnan saying, is the trend shifting to an anti-public cloud behavior from companies? So maybe you can talk about when you'd want to use a public cloud, have GPUs in a public cloud versus hosting them on your own servers, or what are the choices here?
Yeah, so I think it's a matter of companies understand that they need to secure access to GPUs, as I said, right? Like just spinning up and getting GPUs that are out there in the cloud might not be the safe way of getting access to GPUs. So just getting access to those GPUs and securing them, it can be in the cloud, right? You can just buy reserved capacity in the cloud. It can also be on premises. So what we're seeing is this shift, right? Just in terms of people are just securing capacity resources and managing clusters of resources. It can be on premise, it can be in the cloud. In the cloud, again, is that you don't need to manage you don't need to do all the IT in terms of hosting those resources. But we also see this smaller cloud providers as well, cloud providers like CoreWeave and Lambda Labs, who are more specialized for AI, more specialized for GPUs. And we also see like a big demand for their resources. So companies are also going to smaller cloud providers and securing access to resources in those cloud providers as well.
Okay, so really it's a choice, and your IT team's probably going to figure out what they want there. All right. So Joaquin asks, can I use an AI cluster in a Kubernetes environment like Azure Cloud to share resources for LLMs?
Yeah. Okay. So yeah, you can take okay. So in the cloud in Azure, for example, they have you can go with a few ways in terms of pooling resources and creating that cluster, right? So you can pool those resources and you can have those just virtual machines in one cluster. You can install on them a Kubernetes version, right? Like you can install any version of Kubernetes, essentially. It can be a vanilla Kubernetes layer that you manage by yourself. You can also spin up a Kubernetes version of Azure, right? AKS, Azure Kubernetes Service. So you can use that. That will save you a lot of time in terms of installing Kubernetes and doing all the operations around that. So AKS will give you a simple way to create a cluster of a Kubernetes cluster on Azure. Yeah.
All right. So you got Azure Kubernetes cluster, and then that's creating AI jobs on top of that.
Yeah, exactly. So you can think about it that there are like three main layers. So one layer is just the infrastructure, the hardware itself. It can be in the cloud or on premises, as we said. And then you want to have like an orchestration layer. It can be, as we said, like an HPC scheduler. It can also be Kubernetes layer, right? So that's the second layer. And then on top of that, you're running your workloads, right? You're having your tools to run those workloads. So essentially, the straightforward way to launch workloads on Kubernetes is through a command line tool called the kubectl, right? Just applying YAMLs into Kubernetes. So no one wants to do that, right? No one wants to apply YAML files into Kubernetes to launch their jobs, right? So there needs to be this layer of just abstracting all the complexity involved in just launching workloads on top of Kubernetes, right? So that's as we see it, like the tooling layer is the third layer.
Okay. Next question comes from Nuno. See if you can discuss practical terms, the computational cost differences for different workloads, so pre-training, fine-tuning, prompting. Because you mentioned that it's inference needs heavy GPU workload as well as training. So most machine learning models, it's just the training that requires a lot of compute, but this is different. So can you talk about the relative costs here?
Yeah, okay, amazing question. So we will get into that in this part. I think when you have companies, and I'll mention it in a moment. You have companies like OpenAI who are creating foundational models and training models from scratch, right? Like they're using thousands, if not tens of thousands of GPUs. So according to rumors, GPT-4 was trained on more than 20,000 GPUs. So the cost of utilizing 20,000 GPUs is very high, right? When it comes to fine tuning, you typically need much less and much smaller number of GPUs, right? Like maybe you need a few GPUs, right? If you have a lot of data and your models are big, then you might need like tens of GPUs, and it goes like that, right? Like if you have like even bigger data, then you'll need like hundreds of GPUs. But the order of magnitude is around a few GPUs to tens, maybe hundreds of GPUs when you're fine-tuning your models. Depends on the size of the model and the amount of data that you're using. And then when it comes to inference, that's interesting, and I'll in a moment I'll get into the cost of inference and how many GPUs you need just to run inference. It's very interesting, and it's also very compute intensive.
Okay, look forward to that. One final question before we move on. This is from Jonathan. So you mentioned GNV is the community version of your of Run AI. So is that just supporting single GPUs, or can you use multiple GPUs with it?
Yeah, you can use multiple GPUs essentially. You can use multiple GPUs. You can use multiple nodes of GPUs, and then provision them with that GNF tool. Yeah, and you can provision fractions of GPUs within that tool. We're using that tool as well.
All right, super. I think with that, we'll let you carry on with your slides.
Okay, cool. So love the questions. Thank you for that. Okay, so LLM inference. Let's go into that. So I started to spoke about it, right? Like there are a few types, right? Like 3 types of AI activities. One is model creation, right? Companies like OpenAI, Meta, there are not a lot of companies like that in the world who are training models from scratch, foundational models, right? Like they need tens of thousands of GPUs just to train a single model, right? But then there are people who are fine-tuning models, just adjusting existing models into to specific tasks, right? Taking a specific data set and fine-tuning the model, maybe doing full fine-tuning, changing all the weights of that model, maybe doing using fine-tuning mechanism like LoRa and changing part of the model weights, but essentially adjusting the model to do specific tasks using specific data and customizing those models. And then you have this, a third way of just doing prompt engineering, right? Leveraging APIs to interact with LLMs, right? And most of the world is here. Most of the world is fine-tuning and doing prompt engineering. And so fine-tuning, as I said, right, you have your pre-trained LLM, and you're using some domain-specific data set, and you fine-tune that model, right, doing full fine-tuning or partial fine-tuning, and then you're getting a newer LLM, fine-tuned LLM that users can query and get responses, right? You can do also prompt engineering, taking a pre-trained LLM or a fine-tuned LLM, and then users querying that LLM with different in different prompt ways, right? And there are multiple ways to do prompts, right? Like doing task description, just describing the task in those prompts, and giving inputs to the LLM and then getting outputs. You can describe the instructions, right? With like prompt templates, and give inputs to the LLMs and get answers. And maybe you're doing this few shot learning and you're giving a few examples to the LLM and a new input, and then the LLM is giving an output. And maybe you're doing a chain of thoughts, right? Like more advanced prompting. And maybe you're doing a retrieval augmented generation, right? RAG. That's amazing way to prompt LLMs, right? So you have your pre-trained or fine-tuned LLM and you query it. And when you query it, you augment your query with data, relevant data from a knowledge base, right? That knowledge base can be documents that you have in your organization that you want to use with your query, or maybe it's previous chats that you did with the LLM, right? Like just the memory of the of previous chats. And so when you query the model, you can retrieve that data from that knowledge base, and that knowledge base might sit in a vector database, and that query plus that knowledge goes to the LLM, and a response go back to the user, right? So that's another way of just shifting and adjusting the LLM into specific, knowledge base, into specific tasks. So just without fine tuning, without training the model, you can also just adjust and specialize the model answers to your use case, to your tasks, to your private data. But in all use cases, in all of those examples, there is a pre-trained or fine-tuned LLM which is being deployed, right? You have these applications or a user using an application, and you send a query, and you're getting back a result, right? So those LLMs are the costly component when it comes to creating AI applications. Just how to deploy those models and how to control their costs, right? So those LLMs are really costly, and deploying them is really costly, and there are several parameters which are affecting the cost of serving LLMs. And there are a few of them here, and I would love to go over them and maybe give some best practices on how to manage those parameters and manage the cost of LLM serving. So one is model size, quantization, context length, batching, serving frameworks, and autoscale. So let's try to go over them. So first thing is model size, and it goes back to the question of like how many resources, how much compute power do I need for for LLMs, right? For LLM inference. So the answer is that it depends on the model size, right? So for example, let's see that, right? The model size, Llama 2 with 7 billion of parameters and with float 16. So float 16 means that you have 16 bits that are representing each one of the weights, right? Your model has a lot of weights, a lot of parameters. So each parameter is being represented by 16 bits. So essentially 2 bytes, right? And that representation is called float 16, right? The way those 16 bits represent the value of that weight. So the rule of thumb is that a model with 7 billion parameters and float 16 representation will need around double the parameter size, double the model size in terms of just memory on your GPU. So if you have Llama 2 with 7 billion parameters, you need around 14 gigabyte of GPU memory just for storing your model weights. And if you assume a GPU with 40 gigabyte of GPU memory, then it fits into one GPU, and you can host one Llama 2 with 7 billion parameters, float 16 on one GPU, right? If you have Llama 2 with 13 billion parameters, then you need around 26 gigabytes of GPU memory to store the GPU weights. So that still fits into one GPU with 40 gigabytes of GPU memory. But if you're using Llama 2 with 70 billion parameters, and we know from AI that the bigger the model, usually the better the model is as well, right? Like the better the accuracy, the better the results that you get from your model. So we know that bigger is better in AI. So right, so just deploying bigger models might produce better results. But with 70 billion parameters, you need around 140 gigabyte of GPU memory, and that's a lot. So that means 4 GPUs, right? At least 4 GPUs that you need just to run that model. And if you have maybe Falcon model with 180 billion parameters, you need 360 gigabyte of memory, right? So that's something like 16 GPUs that you need, right? So think about it, like if you send a prompt, a query to Falcon with 180 billion parameters, you'll need 16 GPUs, right? Like 16 GPUs will be utilized just to give one answer to one prompt, right? So that's a lot. So think if you have a lot of users, multiply that by 16 GPUs for every user, for every prompt. So that's a lot of GPUs, that's a lot of compute, and that's something to manage, right? So a model size, as the model is larger, you need more GPU memory, more and more GPU. So some best practices on how to deploy models in terms of like which GPU should I choose for my model size. So one best practice is to use what I call the inference GPUs, right? GPUs like T4 or A100, they are available in the cloud, and they typically are more cost efficient when it comes to inference workloads. So those GPUs are typically smaller in terms of the amount of memory that they have and the amount of compute power that they provide, but their price is also much, much, much lower compared to other high-end GPUs. So if your models fit into the memory, the GPU memory of those inference GPUs, try to use them. They are much more cost efficient. Also, their availability in the cloud is typically much better than other high-end GPUs. And use high-end GPUs, right? Like A100, H100, if you need bigger models. So A100 and H100 today come with also 80 gigabyte of GPU memory, and not just 40 gigabyte of GPU memory. There are also versions with 80 gigabyte of memory. So if you have very big models, try to use them. If you can, the models with the GPUs with a bigger model. There are ways to reduce the number of GPUs that are used for inference, even like the bigger models. So if your application is latency insensitive, then you might be able to use less GPUs with ways for, you can essentially store your model weights not just on the GPU memory, but some on the GPU memory and some on the CPU memory. And you can swap the weights between the CPU and the GPU whenever they are needed. So essentially, you don't need like 16 GPUs for running Falcon, but you can use much less than that and store the weights both on the GPU and on the CPU, and you'll need much less GPUs. But that will come with the price of doing more computation on that GPU. You'll have like an overhead in terms of how much time, how much compute you need to run those models. And so if your application is not latency sensitive and not throughput sensitive, it won't help you in terms of reducing the cost the other way around, but it helps you in terms of you'll need less GPUs, right? And less GPUs available to run those models. So DeepSpeed provides this a way to do those things. So check out DeepSpeed, a project by Microsoft, for more information about that. Quantization. So quantization is the number of bits that those weights are being represented, right? As we said, float 16 bits to represent each weight. A way to go in terms of reducing the size of the memory that is needed for those models is just to represent those weights with less bits, right? Maybe with int 4, right? Maybe you want to just use 4 bits to represent each weight. Then you can significantly reduce the amount of memory that you need to store those weights, right? So for example, with Llama 2 with 70 billion parameters, you need just 1 GPU, and with Falcon, it will fit into 4 GPUs. So that's great. That's a great way to reduce the footprint of your weights. But quantization usually comes with a significant accuracy degradation. So your model will be significantly less accurate if you're trying to use such methods. So test before reducing the precision, because the gains in terms of memory are big and significant, but also you might get this accuracy degradation. So test the accuracy if you're doing those things. What we typically see is that models are being deployed with float 16. On the trade-off between memory and accuracy, then float 16 provides, from what we see, the way to go, right? Like what people are actually using. Okay, let's continue. Context length. So context length is the length of your input prompt plus the output prompt, right? You might want to have an LLM with a huge context length, meaning you might want to have like huge queries with a lot of words. Maybe you want to send like full documents to your LLM and ask it, to summarize it or to do, to get insights out of those documents. So if your inputs can be very long, then that's good for you, right? Also, if the output can be very long in terms of like the tokens that are being generated, the words that are being generated, then that's also very beneficial, right? Like you might want your LLM to generate like full articles, full, papers. So as the context length is bigger, you can do more things with your LLM. But longer context length also brings more memory requirement from your GPU, and it also brings more processing, right? So KV cache, maybe some of you heard about it. So with transformers, with language models, the input tokens are being processed and the results are being cached along the way. The attention models in your transformers, they have this caching mechanism with some of the results are being cached. That cache can be very costly in terms of GPU memory. So it's both the input and the generated tokens that are being cached. And the rule of thumb is around 1 megabyte per token that is needed in terms of memory in your GPU for every token in your context length. So for example, if your context length is 1024 tokens, then you need 1 gigabyte of GPU memory. Anthropic, they offer context length of 100,000 tokens. 100,000 tokens, that's huge, that's very long. So for that, you need 100 gigabyte of just GPU memory just to store that cache. So that's big. That's the context length really affect the memory that you need in your GPU. There is another way to go, and without allocating a lot of memory in your GPU for KV cache, you can also recalculate some of the results or all of the results, and then save on the memory footprint. But that will mean that you just need to do more processing, more compute power to spend, and just generating your responses will take more time. So it won't help might not help in terms of cost, but so the context length, wherever you go, you either need more memory or more compute on your GPU. So that affects the cost of your LLM significantly as well. More, so three more things. Batching. Batching is really important. When you're deploying LLMs, take into account batching. That can provide huge benefits in terms of throughput. And throughput means cost of your LLM inference. So GPUs are a parallel machine. With GPUs, you can do parallel computation very efficiently. So as your computations can parallelize better and better, you gain more. Your throughput of your GPU is better, and you're running things more efficiently on your GPU. So batching, with batching, you can batch multiple inputs, multiple sequences, and process all of them together in the GPU in a parallel way, and gain throughput. And gain more efficiency and lower costs. So batching is good when you're using accelerators like GPU. But batching with LLMs for language sequences can be complicated. I want to go over it for a second. So in this figure, there is a great resource here that you can read on continuous batching. But on a nutshell, with batching here, we see like how an LLM works. So the yellow squares over here is one token, is all the input tokens that are sent to an LLM. So here you have 3 tokens sent from the user to the LLM. On the first iteration, the LLM is producing a new token, right? That's marked in blue. On the next iteration, another token is being generated, and so on. So the LLM is this token generation machine, produces one token out after the other until there is an end token, right? Like end marks the end of the sequence, end of the response of the LLM. So a naive batching approach will take multiple sequences, right? Sequence number 1, sequence number 2, 3, and 4, batch them together, input them together to the LLM, and the LLM could parallelize the processing much better, right? But the naive approach, which might be good when you're having models like image models, right? When you're batching images with sequences, with text sequences, it's less efficient because you can see here the white squares. The white squares means that there is no computation being done here. So sequence 2 is longer than the others. So all of those sequences will wait, and we won't have this processing over here because this naive way of batching request only, in a straightforward manner. So all of those white squares are essentially inefficiency when it comes on how to utilize those GPUs, because you could utilize the GPU over here. So if sequence 2 is very long, that can be significant. So people came up with a new way to do batching. It's called continuous batching or in-flight batching. Again, if you want to read all the details, I'll give the slides so you can look it up here. There is some great information here on that, great explanation. So the thing is that you can do batching on the fly when every iteration where a token is being generated, you can batch a new sequence, right? So over here, sequence number 6 is being batched with the other sequences on the fly. Over here, sequence 3 was ended, and automatically you can add sequence 5, and then you're getting much more efficiency out of your GPU, right? Much more throughput. So continuous batching, that's the way to go. Try to use it, can bring, huge value. So batching can bring values, like 10x more throughput, 100 more throughput. It depends really on the size of your model and how much samples you can process in parallel, but it can get into like amazing factors in terms of cost efficiency. Okay. Two last things. So serving frameworks, right? So your LLMs you want to deploy them using some serving frameworks, right? So using some, you want to deploy them in a container, and you need a way to get requests in, process those requests, get the answers back, right? So we like serving frameworks. There are a few, right? There is right now amazing development going on in the community on developing both LLM engines and LLM servers. So LLM engines are those engines, software libraries that are doing these optimizations, hardware-specific optimizations or model-specific optimizations. They're doing, continuous batching and a lot of optimizations relating into how LLMs are being run on a GPU on specific hardware. There are amazing projects like VLLM, TensorRT LLM by NVIDIA, DeepSpeed by Microsoft, and there are more. There are a few there. Extensive development is going on in the community right now, and just on optimizing those LLMs and running them in the most efficient way. LLM servers are those wrappers around the engine. Some LLM servers can support different engines. They provide, an HTTP or gRPC interface. They're providing queuing, a production-grade queuing mechanism. Maybe some of them offer a way to host multiple models. They provide ways to get metrics and monitor the servers. So a lot of capabilities are coming out of the box with those servers. NVIDIA Triton Inference Server is one, Ray LLM, TGI by Hugging Face. So a few of them. There are more. There are many more out there. And so when you're going to deploy your LLMs, so probably you need to choose one of the LLM engines, one of the LLM servers. So try to pay attention of the differences in terms of performance. So latency and throughput are the two important metrics, right? So latency, for example, is the time to first token, right? Like if I'm a user and I'm chatting with my LLM, how much time it takes until I'm getting the first word to my as a response, right? How much time it takes until I'm getting some results. Throughput is, for example, time per output token, how much time it takes to generate tokens on average, right? So that's the throughut. As that time is shorter, both latency and as the latency is smaller, that's better. And as the throughput is higher, you're generating more tokens per second, that's better, right? So try to test those engines and servers for your own use case, for your own models. And compare features that are different features, stability, ease of use. So there's extensive work there. We're also doing a lot of work on just comparing, testing the performance of the various options out there. So we're going to provide some I think, great content around that. So we're going to produce some results, and there are out there also a lot of results that are around, how to choose LLM engines and servers. So that's an amazing space in active development right now. And last thing is autoscale.
Cool. Sorry,
Yeah.
just because we're at time, we are going to carry on and finish this, and there are some great questions from the audience.
Okay, so let's go to the.
Yeah.
I think autoscale is a complex topic. I won't go over it. It's like a huge problem. I think autoscale. Okay. We're also working on that, but yeah, let's go over to. We were working on solving some of these problems here. We're working on just creating an LLM serving solution, right? It's like it's so difficult to deploy models, so we want to help people to do that, in an easier way. So we're working on our solution. That's it. Thank you so much. That's a link to GN and a link to a Discord channel where we call it AI Infra Club. So if you have questions about AI infrastructure, if you want to get information about AI infrastructure, so we're there. We'd love to see you there.
That's fantastic. Thank you so much, Ron. For anyone who has to jump, please do check out the rest of the questions being answered on the recording. You can register for the recording by the link that Reese has been sending through. And before any of you jump, I just want to say we've got 3 related webinars coming up next week. So on Tuesday, there is a code-along session on evaluating LLM responses. You can see how to deal with hallucinations and how to measure the quality of the responses you get from your large language models. On Wednesday, we've got a session on designing data and AI products. So a lot of the success with putting AI into any product is actually with the design of this. And then on Thursday, we've got a session on combining LLMs with knowledge graphs. So we've got 3 exciting sessions coming up for you. Please do go to datacamp.com/webinars, and I will see you again in future sessions. All right, now we've got a few pretty great questions from the audience that I do want to cover. Okay, so this one's from Andres. So you mentioned retrieval augmented generation. Can you just talk a little bit about what the software for that involves?
Yeah. So retrieval augmented generation, so RAG, it involves a few things. So first of all, it involves vector database. Maybe some of you heard about that. So with vector database, you can store your knowledge. Maybe it's your documents, maybe it's previous chats. You can store it in a vector way, right? Like you can create of that data an embedding representation of your data, store it as embedding as vectors in that vector database. And when you send your query to your LLM, you can also transform your query into embeddings into a vector, and with a semantic search, or in some way, you can search relevant information to your query from that database, but just comparing the vector of your query and the vectors of in your knowledge base, and you can retrieve relevant information and augment it to your query. So essentially, you can send to the LLM, a query plus more relevant data, and just like that, orient, just your LLM. So vector database is a new and exciting technology out there, and there are multiple solutions out there. You can look for it. Some great things over there.
Yeah, so for those of you who are DataCamp Workspace users, that's our hosted Jupyter Notebook platform, we have done some previous code alongs on a few different vector databases. So if you're interested in Pinecone or Milvus or Weaviate or Chroma, these are all popular options for vector databases, and we've got some code alongs in there. So please, get registered for DataCamp Workspace. You can do that for free. Check out some of those previous code alongs. All right, so next question is from Nuno. So Nuno's asking about distillation. So can maybe just talk through what's distillation and how does that help you use less GPUs?
Yeah, okay. So with distillations, you can essentially take a big model with a lot of parameters and distill it into a smaller model, right? Smaller model that is more specialized into a specific task. So essentially, there are different algorithms, different ways of taking a big model and view it as a teacher, and then distill it into like a learner model. It's a smaller model that just learns from the bigger model, and it's a smaller model with less parameters, but it's less generic model, but more oriented into a specific, task, specific activity, specific, much more specific. So that's another way. It's like a way to reduce the size of your model in an algorithm way. So there are those ways. There are more ways. Essentially, there are ways where you can prune some of the edges of your model. You can do a lot of optimization just directly on your weights and on how all of those weights are being connected to each other. There are some solutions out there that help you just to optimize the model, make it smaller, make it much more efficient. So there are ways to do that as well.
That seems very useful in a business context. I think with ChatGPT, you can have a conversation with it about anything. If you've got a corporate chatbot, you only want it to just answer customer questions and just in like a professional tone of voice. So you're probably going to want a much more narrow use case. Interesting. Okay. All right. So next question is from an anonymous LinkedIn user. So what's your opinion on larger and larger context lengths? And I know there are some technical problems with long context lengths, so maybe you want to talk about those as well.
Yeah. So that's an interesting topic, right? Because as I said before, I like longer context windows is amazing, right? Your inputs can be longer, maybe the outputs can be longer, but there are some works right now being done in the academia, right, in research institute, showing that the longer the input is, you're starting to get this accuracy degradation. So it becomes harder and harder for the LLM to track the input size, to focus the attention. So people show that accuracy becomes smaller when the context length becomes bigger and bigger. I think it makes sense, right? Like when I'm reading a paper, right, like, and it's a long paper, it's like I'm getting tired at some point. I think it's like if we take an analogy from our own life, the longer the input, the harder for you to concentrate and focus.
Absolutely. So Reese just posted a link in the chat to, there's a paper I read recently on how the accuracy drops in the middle. So if the information it's trying to retrieve is at the start of the context or at the end of the context, it's fine. In the middle is a mess. It's like webinars. You remember the first 10 minutes and the Q&A at the end, and the middle is hard to recall what's going on.
Yeah.
All right. So hopefully that's a problem that is going to get solved. But at the moment, yeah, there are some problems with long context lengths. All right. This one comes from Yukian. Yukian's one of our regular attendees. Can you talk about? Oh, she talked about there were half a dozen different parameters that affect the cost and the performance of these LLMs. So do you want to talk about those?
Yeah,
What's more important?
much more important. Yeah, you'll get. Yeah, I'll say that all of them are important. Of course, the model size is important. We saw that it can the number of GPUs you need for bigger models grows very fast. All of them, I think, context length is important. Batching is really important. Try to use batching if you can. That can get in most common use cases, you can get big value out of just using batching. Autoscale is another big problem, but I didn't touch on it. So I think trying to optimize everything, it's a hard problem, and you need to optimize the multiple parameters while you're deploying LLMs.
Okay, so it's going to be a question of play around, do some tests, and just see where you get some benefits.
I think so. Yeah, you want to use the smallest model that you can and still get like good accuracy, and your model will still perform well. Context length, that's a matter of your application, like how long you want the context window. Try to use batching, right? Like try to different frameworks are out there. There is try to use the best one for you. So there are multiple parameters, I guess. Yeah, it takes some time to deploy models if you want to do it like, in the most efficient way, right?
Okay. All right. Last question then. Can you talk about how orchestration works for reinforcement learning?
Orchestration in terms of cluster orchestrator for compute resource.
Yes.
Yeah. Okay. Okay. Would love if the question was more specific, because with reinforcement learning you mean that a way to orchestrate both the simulations and the training process. Like that's what you have with reinforcement learning. You have the training, and then you're doing the simulation to simulate the model. So maybe that's like, I'm not sure about the question.
Okay, all right. Well, maybe come back to that another time then. All right, sure. With that, we are well over time, so we're going to wrap up there. Thank you once again, Ronan. That was really informative, and yeah, so many interesting issues involved in just getting these models into production and not spending all your company's money on GPUs. Yeah, seems like a challenge. All right, so yeah, thank you again, Ronan. Thank you to Reese for moderating. Thank you to everyone who asked a question. Great engagement there, I have to say. And thank you to everyone who showed up today. So I hope to see you all again in future webinars. Remember, we've got 3 more next week. Please do come back.